Inside this cockpit, a hamster pushes a joystick, operating a fully functional hydraulic excavator. We are testing how a raw forging drive adapts when it is granted the mechanical leverage to reshape the environment. Traditional behavioral science often relies on simple puzzle boxes or levers that trigger a single reflex. These setups are efficient for testing memory, but offer little insight into an animal's ability to manage complex, multi-step mechanical systems. To measure the ceiling of rodent dexterity, we have to move beyond the puzzle box and scale industrial-grade engineering down to a specific, rodent-sized interface. The test site is a custom-built excavation basin filled with a sterile substrate. It provides the resistance of real earth while remaining safe for the animal to navigate. The controls are an exercise in paw ergonomics. Because a hamster generates very little physical force, every lever is calibrated with low-friction seals to ensure that even the lightest touch results in a smooth mechanical response. This diagram shows the core physics of the hydraulic linkage. Moving the control displaces liquid in a small input cylinder. Pressure travels through the line to a larger output cylinder, translating tiny biological movements into heavy, sweeping power. This setup functions as a mechanical bridge, converting a hamster's movements into high-torque industrial output. We start by scent priming the site. Broccoli florets are buried deep within the substrate, close enough to be detected by the hamster's nose, but physically inaccessible through normal digging. At first, the hamster relies on its evolutionary toolkit. It tries to burrow directly into the floor of the cockpit, scratching at the glass and the steel base of the machinery in a frantic attempt to reach the scent. During this scramble, the hamster's weight shifts against the main lift lever. The hydraulic system engages, and the external claw scrapes through the substrate for the first time. Following this accidental movement, the hamster's behavior shifts. It stops the direct digging and begins to interact specifically with the lever that caused the change in the environment. Within minutes, the animal is no longer bumping the controls by chance. It is standing at the joystick, repeatedly triggering the claw to clear the path to the food. To test the limits of this coordination, we increase the stakes. High-value sunflower seeds are now buried beneath a layer of heavy debris and structural obstacles. Simple repetition is no longer enough. This flowchart illustrates the necessary sequence. The hamster must now execute 3 distinct mechanical steps: extension, rotation, and retraction, to navigate the claw around the debris. The physical resistance of the rebel is visible in the hardware. This shot shows the hydraulic piston extending under high pressure, locking into place as the animal holds the lever to maintain the lift. We are watching a collision of 2 systems: the cold, linear logic of the hydraulic hardware and the frantic, biological drive of the animal powering it. The raw foraging instinct has been organized into a strategic protocol. The hamster is now using the machine to solve a problem its body cannot. When the final layer of debris clears, the hamster earns the harvest. Seeds and broccoli are pulled into the operator's reach. While the physical reward is quite clear, the true scientific value lies in the performance data recorded during the trials. This graph tracks time to harvest across 10 trials. The required time plummeted, showing the animal refined its motions. A secondary line tracks the error rate, the frequency of incorrect lever movements. It drops near 0, indicating highly optimized operation. The data shows a transition from trial and error to a state of high-precision operation. The hamster is systematically minimizing its effort to maximize its payout. We often assume that small rodents are limited to a narrow range of instinctual behaviors, but these new trial logs suggest otherwise. Intelligence is frequently a matter of access. An animal's problem-solving capability is often gated by its physical body. Without the right tools, its potential for complex interaction remains hidden. By providing a precise mechanical interface, we see that even a small creature can demonstrate a highly adaptable mastery of the world around it.